this morning is to finish off the bit on the central nervous system by talking a bit about reflexes. Now, I took reflexes out of the exam mainly because the diagram I'm going to draw just seems to confuse people. And it's the same diagram you find absolutely everywhere, but it is quite important to know a bit about reflexes because they are quite a useful way of telling us whether the central nervous system is okay or whether it's been damaged. And doctors will check reflexes, particularly at joints and in the eyes and that sort of thing. And it's just a handy bit to put on here, but it won't come up in the exam. Then we're going to have a look at one part of the nervous system in terms of the actual nerves. If you remember back to the overview of the nervous system, we had this. So we've done most of the central nervous system with just a little bit on reflexes to go, which is largely about the spinal cord, partly about the brain. Then we're going to come back to the nervous system, the nerves of the nervous system, the connections. And we're going to look at the autonomic nervous system as an example in there, or just a branch. The somatic nerves are not really interesting enough to warrant spending hours and hours on them. I will show you a couple of interesting things about them, but we're not going to sort of deal with them otherwise. But the autonomic nervous system we'll look at because it links really well with what we've done on hormones. It's very homeostatic. And hopefully then after break we'll be able to start on the eye. So we will have a look. Sorry, I can't sneeze when I've got a microphone in front of me, so if anybody's listening to this, that was a sneeze. Oh dear. Right. So, back to the bit from yesterday. This afternoon, remember, we are aiming to get that assignment finished. I will go over the whole thing again, just sort of highlighting what you should have in there. Particularly the calculations bit, because I know several people have got themselves in a bit of a hole with the calculations. But to be honest, if you haven't got that completely, well, just finish everything else and hand it in with those partially done. You can always resub on those. Not that it'll necessarily get any clearer in your head over Christmas, but if you just want to be rid of it, then don't worry about that bit. The idea is then that if I'm just going to go over the key bits, and then if you're happy that you've done everything on it, fine. Or if you want to get on with it on laptops, fine. Or if you want to go away and find a bit of the college that's got a computer not in use, fine. And I will sort of wander around as needed if anybody wants particular bits of help on it. But hopefully we'll get that one cleared. Because it's not graded, it's just one to get out of the way. All right, don't be fussing about how good it is particularly. As long as it hits the assessment criteria, that's all you need. So keep checking back at the assessment criteria to see, if you've got what's needed there. Okay, back to the biology. Now, the idea about reflexes, it's a word that's used, quite a lot to just mean sort of very rapid responses, isn't it? And they are responses that don't require any conscious awareness or decision making, if you like. Most of the responses in our body are responses to things that we have awareness of, that our brain's process incoming information. We almost think about it for a little while, or we perceive what's happening, and then instructions are sent out, and we're aware of muscles contracting and that sort of thing. Reflexes are not like that. They operate below the level of consciousness, and they are almost always protective. They're trying to keep us out of trouble. So we'll have a look at a few examples, perhaps. What happens to the pupil of the eye if you shine a bright light in it? It shrinks, yeah. So that's to prevent too much light energy getting into the eye, possibly damaging it, but definitely, it stops you from being dazzled by light. What happens if you overfill your bladder? It'll empty, whether you want it to or not. All right, there is only a limit. Yes, Well, the problem with pregnancy is your pelvis is, they're very cramped, so there's not much space there. So it stretches to sort of emptying point quite quickly. But what happens normally is you've got stretch receptors in the wall of the bladder which fire off to the brain and let you know consciously that your bladder is filling up. And you reach a point where, you decide, yes, all right, it's time to go. Otherwise, presumably, if you leave it too long, the reflex part of the reaction will kick in and your bladder will empty itself. There are two little sphincter muscles. Sphincter muscles are the little ring-shaped ones. We're full of them. I mean, there's one that people refer to particularly, but there's so many more. We'd be in a right mess without sphincters, I will say. You're going to meet several today. That's today's quote. Yes. There are two sphincters at the neck of the bladder, one inside and one outside. One of them is voluntary, but the other one is involuntary. We learn to gain control over the voluntary one, but not the involuntary one. You get to a certain point of stretch where that one will take over regardless. When it very often happens if people have lost a degree of consciousness, doesn't it? If people pass out, then their bladders might empty. The other situation where it happens, it's not where that happens, but it's actually more serious, is related to binge drinking. Alcohol's a bit of an anaesthetic, isn't it? And that could actually numb the nerve endings in the bladder wall to the point where they're not firing off properly. And so even the reflex emptying doesn't happen because the information's not firing off. And what happens to the bladder? It will burst. Burst bladders from binge drinking are actually an issue. So they're, these reflexes would be protecting us against that. And then other reflexes that people have got sort of familiarity with, if you hurt yourself, if you touch something hot, what do? Yeah, you pull your hand away before you do anything else. You pull your hand away before you even know it's hot, don't you? So, if you touch something in the kitchen, your hand is away before you sort of register on what's happened. Similarly, if you stand on something, all right, here is the debate we raise every year. What is the most painful thing to stand on? Lego. Right, it's always a debate between Lego and the 3-pin plug, yeah. Every time, yeah, plugs and Lego. It depends on what sort of Lego, I guess. But yeah, it's always between those two. And the first thing you do is pull your foot away, don't you? Yeah. Yeah, I mean the shouting at it and the cursing and stuff comes afterwards. And if you've touched something hot, it's then the shaking it, blowing on it, putting it under a tap or whatever. So those are protective. The reflexes are the bits that pull yourself away. And then your brain gets to know about what's happened and then kicks in with a bit more help to deal with any possible after effects. But the immediate pull away, you don't have any control over that. The other one that people are most familiar with is the reflex in our joints, particularly the knee joint. That's right, yeah. The knee jerk reflex, where they tap. You cross your legs over so they cross at the knee. That stretches the tendon just under the kneecap. And if you tap that so it stretches it a bit more, that should make the muscle in your thigh contract and make your leg kick. You have to position it quite carefully. But actually, you could do a similar thing at all the joints. It's just that that's the most obvious one. So if doctors are trying to test whether there's damage to the brain or the spinal cord, they'll go around tapping joints on both sides to see if the little tension that you get is the same. You think, well, why have you got that there? Why does your knee need to kick forward? Is it a reflex that you need if somebody, are we protecting ourselves against these, I don't know, gnomes that leap out of bushes and headbutt us in the knees or something? No. It's to do with walking. If you think about what happens to your leg at the back of a step, your leg, when you've finished a step, is out at the back. What do you then need it to do? Come forwards, kick forwards. Otherwise, you're going to fall flat on your face, aren't you? So it helps to bring your leg forward as part of the walking movement. And it's also protection against overstretching joints as well, some of the others. So reflexes are really useful things. You can learn. There are what we call conditioned reflexes. I don't think that comes into psychology, the psychology that you do. But conditioned reflexes are ones that you're not born with, but that you learn. I suppose like the control of the bladder, that's or even a reflex in that sense. But things like, the classic, anyone heard of Pavlov's dogs? Yeah? Yeah, Pavlov fed his dogs and rang a bell at the same time, and they associated the sound of the bell with the arrival of food, and after a while he could just ring the bell and they'd produce saliva expecting the food. Simple as that. They learned that. They learned to associate the bell with the food. There are, the reflexes like the eye and what have you that we're born with, we keep throughout life. There are some that we're born with that small babies have that they lose. One of them is the stepping reflex. Anyone seen that? Newborn babies. Yeah, that's right. Newborn babies, particularly if you put something against their shins, will step over it. Their tiny little legs are making stepping movements. And it's a reflex that they don't have for very long. It's no use to them at that age, but they have this odd stepping reflex. The other thing is, in order to do that, most of you would probably think, oh, you hold the baby under the armpits. But how else can you hold a newborn baby? Quite strongly. They will grasp your fingers strongly enough for you to actually lift them. Most people wouldn't want to do it, but you can do it over a bed or a cushion. You can prove that grasping reflex. And why have they got a grasping reflex? Where do we come from? What have we evolved from? Hairier animals. So a newborn baby needs to be able to hang on to mum's fur. There's not many mums that I'm aware of, who are that furry, but, it's there just in case. But they grasp clothes as well. But, most people, faced with a newborn baby, one of the first things you do is you put your finger into its hand, and it goes like that. But that goes as well. They can't be grasping absolutely everything. But, yeah. So those are reflexes they're born with that they lose. There are other reflexes that can be learned. And then there's all these ones that just generally protect us. So they are quite useful and interesting things. They use the pupil reflex, don't they, as a sign of brain damage. Pupils uneven and, pupils blown, that sort of thing. Doctors will lift an eyelid, shine a light into the eye, and if the pupil constricts, that suggests that the brain has still got a chance. But if they just dilate, it means that the muscles in the eye have relaxed and that the eye is not responding to light anymore. So, that suggests if that reflex has gone, the brain is not in a good way. And if they're uneven, it suggests that there's damage on one side. Of course, if they're both gone, then, it's a bit more catastrophic even. So I'm going to try and show you how a reflex works. The thing about the actual reflex itself is it may involve as few as 2 neurons, literally. 2 cells, that's it, 2 nerve cells, no more. Usually it's 3. The ones that go through the base of the brain are very often 2, I think. The ones that go through the spine are 3. I'm going to draw one that's got 3 in it just so that you can see the bits. I gave up handing out diagrams for this because people would look at them and just wouldn't see what it was. So I'm going to build a diagram, which, if you want to draw it, that's fine. It won't come up in the exam, so, you don't have to worry about it if you don't quite get the diagram. But, you can see why the idea of reflexes is important. Okay. So rapid protective responses not involving conscious awareness Now, let's, what we need to start with is the spinal cord, and this is why I'm doing it in here, because we've done the brain. And the spinal cord itself, there's not a lot to say about it. It is just a big bundle of nerves. Now, as far as the top of the lumbar region, these nerves are bundled together to form one solid nerve. Below the thoracic vertebrae, into the lumbar region and lower, they form like a, well, it's known as the horse's tail, the cauda equini. They're loose nerves in there, but they are really just a communication between the brain and the rest of the body. And if you take a cross-section through the spinal cord, never mind the bones, what you get is, oops, the cross-section is a bit like this. That's, yeah, all right, I've got the nerves going in and out, I've got them a bit wonky. There is a distinct area inside which is identifiable, and a little channel running down the middle of the spinal cord. What might be in there? Sorry? No. It's fluid that runs down there. They call it cerebrospinal fluid, CSF. It circulates around, it goes in the brain, it goes around the spine, and if they do a lumbar puncture, they draw some of that fluid off. Yeah. Right, now what you've got here, let's just get this clear. I haven't put the bones around it, so this is just spinal cord. The two areas we can see here, the inside area is mostly cell bodies or relay neurons. And because of that, it doesn't have any myelin around it and is known as grey matter. Around the outside, you get all the myelin of the fibres, and that's called white matter. Now, where have you heard of grey matter before? Brain, yeah. With the spinal cord, the grey matter's on the inside and the white matter's on the outside. The brain, it's the other way round. The bit that you see is all the cell bodies on the outside. That's the grey matter. That's why we call it that. And then the fibres come in the middle. So the white matter of the brain would be where it connects into the brainstem. So that's our spinal cord. Now, I'm going to need a stimulus of some sort, so I'm going to put a finger going into a flame. So let's have our finger over here. Now, the problem people have with this, I think, is that the parts, I'm going to put these three parts on here, which are completely out of scale, and they don't connect up properly. So, a finger. I'm thinking, how is that a finger? Whoops. It is a finger, sorry. Yeah, I'm sorry, I can't have a finger like that. That's just not normal. Right, now it's a finger. And the finger, for some reason, known only to the owner of the finger, has gone into a flame. Right? Oh, I think I'll stick my finger in the flame. Oh, most people do it at some point. So that stimulus, the flame, is going to be detected by sensory receptors in the skin, which will connect to the sensory nerve, the neuron, that's going to go to the spinal cord. However, there's then just a shortcut through a relay neuron, and an impulse comes out through a motor neuron to make a muscle contract, to pull your finger out of the flame, because it wasn't a very good idea. So down here, I'm going to have a muscle. All right. So this is the tricky bit, is that, you know, people just don't get what's happening here. So this is our muscle. This is going to produce a response. It's going to contract and pull your hand away. Here we've got our stimulus. Our sensory receptors. Okay, I need to complete this over here a bit. Coming out of the spinal cord, we have nerves. That one has a lump on it for a reason. This one doesn't. Whoops. So these are badly balanced. and it'll be the same over the other side. And what happens is that the stimulus is detected by sensory nerve endings. They are part of a sensory neuron which goes up your finger, through your hand, through your arm, into your shoulder, across your back and into the spinal cord. Now, on a sensory neuron, if you remember when we did it for the structure, the cell bodies are part way along and they all gather at the same place. So you get little swelling on the nerve where the cell bodies are. And it goes into the spinal cord like that. And we're going to make a synapse at that point. So that's one neuron. That's it, one neuron from the tip of your finger into your spinal cord. So this is a sensory neuron. There is then a very rapid connection through a relay neuron that doesn't really have much length to it. Relay neuron across the spinal cord. I'll label that in a minute when I know how much space I've got. And that synapses with a motor neuron that comes out. Whoops, I didn't leave enough space for that. And connects with the muscle. And that's it. That's what we call a reflex arc. An arc being a curve that goes in, comes out. So the green one is the motor neuron. And the blue one is the relay neuron. I'm just going to label it in there to leave myself some space. All right, so that is literally all that's involved in pulling your finger away from the heat. However, you usually do something else as well. You might swear, you might wave it about, you might blow on it, you might put it under the tap. And so somewhere in all this, the brain must find out what's happened. Not immediately, but it does find out. So we actually need another connection that goes to the brain. And so we will have a purple connection. I think it goes on here. Just need to get that going into the white matter bit. But this is our connection to the brain. All right, so that's a dashed line for that arrow. It's just started at that synapse, so we've actually got a double synapse here. This sensory neuron is passing information to the relay neuron, but at the same time, you're getting a connection that passes the impulse on to the brain. So the brain gets to know about what's happened and can take a little bit more elaborate sort of action to deal with the possible consequences. And so that's, the simplicity of reflexes. And what I used to do as an exam question, I think I'd start the diagram with the sensory neuron just sort of partly drawn, and then leave the bit for completion inside the spinal cord and say to students, fill in this diagram, complete the diagram and label it. And for some reason, people used to connect the sensory neuron up to the outside of the nerves, the black lines on there, and just didn't get it. And it is tricky. And I think the only way to get any understanding is to do what you've just done, and that's to draw it yourself. But even so, it's just so, you've got a finger, you've got a spinal cord, and you've got a muscle in your arm, and they're not attached to each other in any way. So it is really quite hard to get your head round. But these are just notoriously awkward, but very, very important. So, if you want to put any examples on there, we could put the pupil reflex. I think that's one that it's worth you knowing, isn't it? the knee-jerk reflex. So when you, use the word, it's got a very specific meaning. There's a difference between reflexes and just rapid responses that we've learned, I think, really. I mean, you think about when you learn to do stuff, say, like driving, for example. Oh, did that as a reflex. I suppose sometimes it might be, but you jam your foot on the brake if you saw, somebody crossing the road or that sort of thing. But we talk about your reflex type or reflex, I think, when you were doing the dropping the ruler, testing your reflexes. That's not a useful reflex particularly. Morning. Good. Catching a ruler because it's dropping is not a particularly useful reflex. You've got the conscious awareness of that, so that's not a reflex, is it? That really wasn't, testing your reflexes at all. It was just measuring your reaction time. So there is that difference between rapid reactions and reflexes. Okay, that's that bit done. It won't be in the exam. You don't need it for that, but it just builds your understanding, I hope, of the nervous system. Okay, now moving on. Let's just go back again. I'm sorry, I keep going back to the starting point with this. Gone way too far. Central nervous system, sort of covered. Next job then is to look at nerves. Now the thing about nerves is you can classify them in a lot of different ways, and this is just sort of the most obvious way. We could, for example, just start by doing sensory nerves, motor nerves. What's the difference between a neuron and a nerve? Well, a neuron is a cell, and a nerve is a bundle of these things, usually with a myelin sheath around the outside of them. So you could have you could have tens, hundreds, thousands. It depends on the size of the nerve. But that's a nerve. That's all a nerve is. It is a bundle of neurons. Now, the somatic nerves, I'm not going to do any notes or diagrams or anything on this, but I'm going to show you a few things because it is an interesting sort of aspect to this. The somatic ones can be sensory or motor. So, sensory ones would be things like the optic nerve, for example, going from your eyes to the visual area of your brain. Plenty of other cranial nerves, as we call them as well, that supply, sort of give us information about, well, there's the sense of smell, the sense of hearing. These are all sensory nerves that, we're aware of their function. Motor nerves would include ones that, cause contraction of muscles. Sciatic nerve is a good example, the one that goes down the leg. And these are ones that carry out conscious response. Now, the sensory ones, let's get back to, I think I'll just use the internet. I'm not actually going to put these things into the file, but I'm just going to show you a couple of things in relation to these nerves. The sensory ones originate in sense organs and sensory receptors, don't they, like eyes and skin and stuff like that. Now, the skin is quite an interesting one, isn't it? Because different parts of the skin have got different numbers of sensory receptors, haven't they? So which bit of the skin is most sensitive? Fingertips, yeah. Somebody yesterday said, is it the end of your nose? Lips are quite sensitive, but you've got to think to yourself, if you wake up in the dark and you're trying to find the light switch, you don't use your nose, do you? Or if you're a blind person and you wanted to learn Braille, for example, you ain't going to use your nose or the back of your arm or your knee. You use your fingertips. So the fingertips have the most sensory nerve endings, and so consequently they have quite a lot of space allocated in the brain. And there are diagrams that show you the relative number of sensory nerve endings in different parts of the body. And they're quite entertaining. You'll like these. Have you ever heard the word homunculus? No. A homunculus is a little person, basically. There's an example. Yeah, it's not big enough. Okay. So that is a human body drawn to show the relative sensitivity of the different parts. This is showing that there's the sensory nerve endings, the sensory nerves as part of the somatic nervous system. So you could. It's not hugely so. I know. It's not as sensitive as you might think. Well, it depends what you started with, doesn't it? Really. But it's not as sensitive as hands. I mean, again, you probably wouldn't use it to find a light switch or read Braille. If you come across anybody who's using that as an excuse, it's not on. You've seen the diagram. It's not as sensitive as your fingers. So stop it, put it away. Use your fingers. That's going to be a useful phrase in a lot of scenarios. All right. But your hands mostly, obviously. Lips, and then variety of other bits, and there's quite a lot of areas there that are very low sensitivity. Now, the thing is, all right, we're not studying this as such, but of course it has huge relevance to those of you going into nursing, doesn't it? In terms of where people feel sensation in terms of pains when they're ill. Oh, well, pinching the ear, because it's sensitive, will actually sort of tend to bring somebody sort of out a bit if they're, if they are sort of just below the surface. But it's sort of significant to things like pressure sores, isn't it? Because, it's the bits of the body that aren't very sensitive that are most prone to pressure sores, aren't they? Because you're not feeling it so much. So, typically it's sort of backs of heels and hips and the base of any bony bits, elbows. So, all the bits that don't really have much sensation. And that sort of makes sense, doesn't it? Absolutely. Yes, yeah. So, because there's not much there in terms of sensation. Feet are not terribly sensitive. I mean, they need to be sensitive in order to, detect what's on the ground and whether you've stood on something sharp and that sort of thing. And the Lego, we had that one. Lego or the 3-pin plug, we decide. But you also have the issue that people with diabetes lose sensation in the feet. I think it's related to the damage to the capillaries, the blood vessels, which are then not supplying the nerves, so the nerves get damaged. Yeah? Yeah, I think when anything that affects circulation will then also affect the nerves, because the nerves rely on good circulation. So with people with diabetes, you have the issues of them having amputations, don't you? Because already the feet are not hugely sensitive, but then you put in the damage there, and they don't notice when they've got sort of deep cuts or infections or split skin and that sort of thing, and and just wouldn't notice it necessarily, and don't heal either. So you've got number of issues there with that. The other way that you can map this out over the brain, you can map it out over the brain. Let's have that one. Oh, we don't want that one. That's actually just for touch and pain, that one. What I actually want is, I want one of these ones. That's not so good. I want one that goes across the whole brain. That one might do it, actually. This is a different sort of version of the same approach, where it's actually mapped over the brain surface. This is the sensory allocation of nerves on the left, whereas the one on the right is the motor nerves. And over the surface of the brain, you're looking at that particular strip. That is exactly where it is. You can see which bits are where, but also in terms of size, the amount of area that's actually allocated to specific parts of the body. Now, sensory, we've got sort of quite a lot for the first finger in comparison with the other fingers. Quite a lot on the foot, actually, in that one. Quite a lot of space, and that's where it sort of folds in. That's not a particularly clear one, that one, but, that's just it's another approach. But this one also gives us the motor view as well, how much nervous system is allocated to moving bits of us. And you can see, obviously, there's a lot allocated to the hand because, there's a lot of precision. Even in just writing, you think about how long it takes you to learn to write. And then people who have other skills, that are hand-based sort of crafts and sewing and all that sort of stuff. So the hands, they have quite a lot of motor attention paid to them. And then, of course, the mouth and the lips and the jaw generally because of speech, needing to actually control that. So there's quite a lot of brain associated with the control of speech. So those are sort of interesting bits about the allocation of those things. Something else, I've got several sort of diagrammatic things that are useful here. If you've ever suffered an injury to your back or your neck, you might not immediately know because you might feel pain or numbness somewhere else. Now, I have a classic example. I've got an injury in my neck from nearly 20 years ago now, which is just compounded by wear and tear because of my age. But I didn't realise I'd done anything in my neck straight away. I'd got numbness in my fingertips, and I thought I'd got a rose prickle in it or something like that out of the garden. And it wasn't until I got it looked into, probably about a year or so later, by which time, of course, damage is done, isn't it? That I discovered actually, of course, it was coming from my spine. And you find this with pains, and I mean, sciatica is a classic example, isn't it? The sciatic nerve comes out of the spine and down your leg. It's not your spine that hurts. Yeah? Yeah. It depending on how bad it is. It's sort of similar to what I've got, and what I'm using the TENS machine for at the moment. That it goes down one leg, and you can actually map these nerves out. The sensory nerves that come out of your spine can be mapped into different parts of the body. Now, where they come out, if you have a look, I'm not going to go over to the model because I wander too far from the recording system if I do that. But if you have a look at that spine model, you can see nerves coming out of the spine. Yeah? So where are they going? Well, some of those nerves, the little yellow rubbery bits sort of sticking out in the back, if anybody wants to just sort of rotate it round a bit, you can give it a wiggle. That's it. So that's it. The little rubbery bits sticking out of the holes there, those are the nerves. Now, some of the nerves are going in, sensory ones. They're also coming out. They are where I drew on here. Let's go back to my reflex. Those yellow rubbery bits are these. All right, so this thing here is the yellow rubbery bit. That's a spinal nerve on there coming out. All the other stuff's happening inside. All right, but that's what those are. Now, they come from and go to various parts of the body, but because they're coming out all the way down the spine, you can actually sort of map out where they go. And it's done on a sort of basis of dividing up the skin, if you like. And you get this sort of effect. I'm going to just take the first one because it's good on Wikipedia. Oh, come on, I need to fit on the screen. I think it fits on the screen at 100, yes, it does. Let's move that back now. And what we have coming down here are the different spinal nerves identified. So we know exactly where they're coming and going from. Now, in terms of the bones of the spine, we don't do the skeletal system. It's interesting, but, it's a system that's very easy for you to study yourselves. In the neck, you have cervical vertebrae. There are 7 of them. 2 at the top help with articulating the skull, and then you've got 5 in your neck. There are then 12 thoracic vertebrae that your ribs are joined to. You've got 5 lumbar vertebrae in the small of your back. And then you have 5 sacral vertebrae that join together to form a plate called the sacrum. And of course the good old coccyx off the bottom, several little bones that usually curl under. In some people they curl out. You can get a little tail sort of effect. And this is the time of year when you find out about your coccyx. If you slip on the ice and you land on your bum, you'll find your coccyx, won't you? You know, people break them sometimes. It'd be really uncomfortable sitting down for ages. But this maps out where these nerves are going, the nerves that are associated with those bones. The cervical ones, you can see, they're going up into the head. But we've then got C5, C6, C7 and C8, cervical 5, 6, 7, 8, come down into the arm. Now, I was getting numbness in my first 2 fingers, which are supplied by C7. So that would tell me, you know, because I've got numbness in those fingers, I know there's a problem with the C7 nerve in my neck. And there is. So, you know, I've had it MRI'd and all sorts, and yeah, can't do anything about it. Basically, it's, well, yeah, wear and tear. Yeah. If it had been my outer 2 fingers, it would be C8. You know, it's a different nerve. So they're very, very distinct in where they go. Coming further down, you've got the nerves that go into the leg. All the thoracic ones only really go to the muscles between the ribs, the intercostal muscles. So they don't have any other sort of locations. You then get down into the lumbar ones, and I can't remember which one is the sciatic out of these. I'm feeling it's probably S1, sorry, below the lumbar. I think it's probably S1, not sure. But I think S1's the one I'm having trouble with now. S2, or you've got S1, S2, and then you've got S3, 4, 5, which are basically supplying bum. Pelvic floor, I suppose, would be the best description. So ladies know all about pelvic floor muscles, don't they? But those muscles from the sacrum supply the pelvic floor. So that's another way of mapping out the somatic nerves. But that's really about all there is to say about it. And it's not, these are not to do with any homeostatic function or anything like that. These are just, they've got this aspect of interest. And, you know, if you're going into healthcare professions, you are going to meet, you know, implications of nerve damage or pain or, you know, things like that. So it is worth being aware. You know, if somebody says, oh, I've got real pain in my leg, that's not necessarily a pain in their leg. It might be coming from the spine. Or, you know, numbness in the fingers. It might have nothing to do with the fingers. It might be coming from a nerve in the neck, and so on. So we're going to leave the somatic nerves at that. I'm not doing anything else on them. That was really all the attention they got. But the other part of the nerves is the autonomic nervous system. So I'm going to spend a bit of time on that. I hope if I wrote it rightly, autonomic. Now what I need is, I think I've used the same ones I used yesterday. I've taken out the image of this that I used to put in the handouts as well. Slightly bigger than I need it. Because this, I don't think this comes up in the exam either, but this is, it's just useful to go with the idea of hormones. So I'll spend a while explaining through this. The autonomic nervous system, well, auto means self. So it's, you know, it's controlling the self, if you like, the internal state of things. So it's very much concerned with homeostasis. And these autonomic nerves, they leave the spine, actually, and the base of the brain, alongside those somatic nerves. So I suspect the ones that are on that model are just the somatic nerves. But then, in addition, you have autonomic nerves, right? So they're not the only ones that are there. The autonomic nerves work automatically, and these are the ones that operate under our level of consciousness. They're controlling things like heart rate, breathing rate, blood supplies to things, pupils being constricted or dilated, that sort of stuff. So not things that we've got control over ourselves, all right? But they are, you know, working away in the background all the time in order to maintain constant internal conditions. Now, there are two divisions, as they are called, and I'm just going to go over those, and then I'll move it up the board and make it a bit larger so you're in with a chance of seeing it. You've got, on the right, you've got the sympathetic division. Now, sympathetic makes it sound like it's calming, doesn't it? No, it isn't, because what does it say underneath? Fight or flight, which is like the hormone adrenaline. Yeah. So the sympathetic part of the autonomic nervous system is actually sympathetic to adrenaline. It actually works in the same way as adrenaline. And it's this bit that kicks off before adrenaline gets into your circulation, because adrenaline is a hormone. It's got to be released from the adrenal glands. It's got to circulate in the blood and get to the tissues. So, you know, you can't wait for that if you need to respond to danger. So this kicks off first, and part of what this does is to trigger the production of adrenaline. So that's the sympathetic division. Now, the nerves for the sympathetic division come out of the spine alongside those that are on there, alongside thoracic nerves, lumbar nerves, and they go to their organs. They're only motor nerves, these ones, they're not sensory. These are, you know, running alongside the thoracic and lumbar nerves that supply all the other bits that we've just been looking at. But these are just about homeostatic control. The other division is called the parasympathetic division, and I like the comparison here is rest and digest. So you've got flight or fight, or flight, yeah, fight or flight. You can't have flight and fight, can you? Doesn't work like that. Flight or fight is your, you know, stress response. Rest and digest is equally necessary, you know, the digest bit, think about it. But, you know, you can't have them both working at once. So they're constantly sort of, you know, switching in, switching out. And we've got a balancing act going on between them all the time. So I'm just going to move that up a bit, so get rid of that bit at the top, and hopefully just make it a little bit clearer. I don't know if that's going to help a lot. Right, that's about the best I can do with it. Now I shall forget which is which. I'm going to start on the right hand side, because it's a little bit easier to understand what the sympathetic part does, and then to, you know, to look, I don't know, I might just actually, rather than one side then the other, I might just start at the top and work down, rather than have to do the same structures again. If we start at the top then, we've got the pupil of the eye. Now, we're going to meet that later this morning. The pupil of the eye is the black bit, the hole that lets light in. Now, we just said that in a reflex, if you shine a light in the eye, the pupil constricts, it gets smaller. But that's not the only reason why it might do that. It does actually dilate in response to stress. Now, it's rather a bizarre thing, and we were trying to work this out yesterday, that I think they say that pupils dilate when you really like somebody. It's a sign of attraction that your pupils dilate. So I'm not sure how that then tallies with this idea of being under threat. So, you know, if you look at someone and their pupils dilate, it means they like you. But it also could mean they're scared of you. So I'm really not sure, you know, quite how that works. But, you know, responses are strange things. They're never quite just one rule for everything. If you are under threat, let's say, you know, you've been pinned in a corner by a lion, you know, it happens a lot around here. and yeah, you're going to need to look for an escape route of some sort, then dilating the pupils will allow more light into your eyes so you can see better, basically, is the principle behind that. Whereas if you're just relaxing and not needing to do very much, then the pupils can afford to be constricted. You can moderate the amount of light entering the eye, so the parasympathetic kicks in there. Okay, moving down, the next things here are supposed to be salivary glands. And, well, the fact that the one on the left, the parasympathetic, is also entitled rest and digest will tell you, yeah, they need to be active then in order to digest food. So the parasympathetic nervous system will stimulate the production of saliva, but of course the sympathetic nervous system stops it. So when we are really stressed and nervous, we get a dry mouth. Yeah, spot on. But you can't have them both at once, can you? Well, it wouldn't make sense. So, you know, you've got, I'm not sure why that would be particularly helpful. I suppose it's just not wasting your resources. You know, or perhaps if you're being threatened by something big and hairy, you know, you don't want to be dribbling. Yeah, sometimes the actual reasoning, you know, is not obvious. It's more that it's useful when you're resting rather than, you know, it needing to be switched off. I think it is really about just use of resources in the body, you know, conserving your supplies and everything. Right, if we now come down to the next one, it gets a little bit more obvious that we've got a heart here. The heart is perfectly capable of contracting and pumping without the need for a nerve connection. The heart muscle does not contract because a nerve tells it to. You could, theoretically, take a heart out of a body and it will keep contracting. You've got to supply it with enough nutrients and oxygen, though. Well, yeah, I mean, hearts will function as long as they've got enough oxygen and glucose, really, I suppose. So they need a blood supply. And this is one of the things I was listening to. There was an article on Radio 4, I can't remember where I was driving, where they were talking about artificial hearts, because you would think, wouldn't you, that artificial hearts ought to be really quite straightforward. They're only a bit of plumbing. The problem is things like with metal and plastic, it increases the risk of clots. But the other thing is the reliability. You know, you can't afford for them to break down, ever, at all. But they were saying, actually, rather than trying to develop artificial hearts, and I think it was in relation to this change that they're looking at in terms of organ donation. Yeah, so they're looking, I'm sure you all know, they're looking to change it so that you actually have to opt out rather than opt in, which I don't think is necessarily a bad idea at all. They said, you know, at the moment there is just a dire lack of hearts. You know, there are people on the waiting list, you know, who die on the waiting list, aren't there? Because not enough people say yes. But apart from that, you also have the issue that because you've got to match up the tissue types, you very often have to transport the organs, don't you? So you get, you know, they might be transported by helicopter and motorbike and all sorts, you know, way across the country. And that's where the problem lies, in actually keeping the organ alive. And so they were thinking, they're looking at ways of actually, you know, increasing the amount of time that the heart can be out of the body, in terms of providing the heart perhaps with an artificial circulation when it's been taken out of the body, connecting it up to some, you know, way of supplying nutrients and oxygen and stuff. But they wouldn't have to supply a nerve because the heart contracts without a nerve. They don't particularly want it contracting while they're transporting it because that's just using up its resources. And they'll usually get it down to where it perhaps contracts, I don't know, once a minute or something like that. But, you know.
Like when someone dies, how long have they got to get the heart out for it
to actually take it from the donor to the recipient? Yeah. What they normally do with the person who's died, the donor, is usually going to be on a machine that will keep it ready until the latest possible minute, because I think it's something like about 3 or 4 hours maximum. And if you've got to put the transport time into that, you know, by the time you've spent an hour transporting it, well, you've got to get it out, you've got to pack it, you've got to transport it, you've got to unpack it, you've got to check it, you know, before the operation can take place, and that could be several hours, you know. And the awful thing is, you know, you've got to take the malfunctioning heart out of somebody, haven't you? You know, in the hope that this one's working okay. But yeah, it's actually not very long, is it really? Yeah, I think it's about that sort of time scale. So,
My mother-in-law had a liver transplant.
all right, yeah.
And yeah, she was one in the middle of the night.
Yes, this is it. The sort of,
At match,
yeah.
had to go.
It is. It has to be very, yeah, yeah. You have to be standing by and yeah, just ready to jump at any moment. But it's not, you know, the nerves are not an issue because the heart doesn't need a nerve. However, it has nerves connected to it. Obviously, from here, it's got autonomic nerves. It's got sympathetic and parasympathetic innervation, we'd call it. That's not innervation, it's innervation. Nerves attached. And you think, well, why do we need that? Well, there is a small area of the heart that controls the contraction. The contraction starts at one point. All right, we'll meet that when we do the heart. And the nerves are connected to that, really to act as an accelerator and a brake. That's all. Now, if somebody's had a heart transplant, they are not going to have those nerves connected. You can't stitch nerves up. It doesn't work. But they rely on things like body temperature and adrenaline and things like that to control their heart rate. But normally, if we are running our own hearts, then we have the actual uncontrolled rate for a heart is about 200 beats a minute. So actually all we need is a brake. We only need to slow it down. And so what happens with the parasympathetic system is that it puts the foot on the brake and slows down the contraction, whereas the sympathetic stimulation takes the foot off the brake and increases the rate. So that will help us deal with stress because it will get the oxygen around the body quicker, you know, it will get the blood through the lungs quicker, through the muscles quicker and so on. So it will get oxygen to our respiring tissues. And then similarly, of course, if we're going to be wanting to get oxygen and nutrients around the body quickly, then, well, from the oxygen side, we need to get the lungs working effectively. So we've also got nerves going to the lungs, and the flight or fight bit, the sympathetic part of this, it says on here, facilitates breathing, which means makes it easier. It will increase the rate of breathing, it will increase the depth of breathing, it will dilate the airways, so you're just getting more air move in and out of the lungs, so the oxygen can get into the blood, be pumped by the heart, the carbon dioxide can get out of the blood and be breathed away. And so, you know, it makes the work of the heart actually have a meaning. Similarly, you know, if you're relaxing, then the airways can constrict and the rate can drop and the depth can drop. It's not so critical. So we, you know, not wasting our resources on a system that's just ticking over, really. Now, when we come to the next two, we've got a stomach and liver and gallbladder here. And I'm not certain that the liver itself has a nerve supply, but it is on here, so I'll go with that for now. But the stomach, definitely. Now, flight or fight, sympathetic nervous system. Is your stomach really, you know, good at digesting stuff when you're nervous? No. You might get indigestion. You might, if your stomach's empty, you might get butterflies. It churns, doesn't it? It goes tight. You know, you feel that tension in your stomach. And that's because you've got this sympathetic stimulation of the muscle wall in the stomach. Now, for the parasympathetic stimulation, of course, you know, if this is rest and digest, then, that's what it's there for. You know, it is actually to encourage the stomach to get on with its job. So you can't have the demands of stress and relaxation on the stomach at the same time, like anything else. And this is why, you know, you're advised not to go swimming for an hour after eating. Because the swimming bit is, you know, when it's exercise, that's going to actually require blood to go to your muscles, whereas the digestion bit requires the blood to go to your stomach. So you can't do both. So although people say, oh yeah, you know, you'll be sick or you'll get indigestion or you'll get cramp, It's more about the fact that you're not doing either thing very well because the systems are sort of battling it out. So, you know, you do put yourself more at risk. I mean, if it's only, you know, a sandwich or something like that, it's not a big deal. But if you've eaten a 3-course meal, you know, and mince and coffee and, I don't know, cheese board and, well, then, yeah, you don't go for exercise after that, not straight after it. Although most people wouldn't want to, would they? Yeah, prepare for that in, you know, about 10 days. As far as the liver and the gallbladder are concerned, on the right over here, we've got, well, several nerves claiming that they supply the liver and cause the release of glucose. What substance will the glucose be released from? Sorry? Glycogen. Yeah, glycogen is stored in the liver as glycogen, and normally glucagons, the hormone that would release it, and adrenaline would have a go as well. But we have here got, I suppose, yeah, when you consider adrenaline would do it, the neurotransmitter in the sympathetic nervous system is actually noradrenaline. So it's doing the same things. I suppose that's fair enough. But yeah, I've just never been aware of a nerve to the liver. But yeah, presumably it does. But that will give us rapid glucose into the blood without having to wait for hormones. On the other side, however, once you are rested and relaxing and able to digest, then parasympathetic stimulation will give the gallbladder a kick and say, yeah, you can squirt some bile out and that'll help you to digest fats. And, you know, that's something that's best done when you're not trying to do anything else. Fats take quite a lot of digestion. The problem is, of course, fat and water don't mix, do they? Most of the contents of the gut is going to be watery, and fats would literally just float on the top or as droplets. So bile acts like a bit like a detergent, and it breaks the fat droplets up into tiny bits with a much larger surface area so that you can digest them. Right. I didn't point out actually that parasympathetic ones come out alongside nerves from the brain, so cranial nerves and down at the sacrum. So yeah, we've got a bit of a separation as far as the autonomic nerves are concerned, whereas cranial nerves and spinal nerves come out all the way down. We've got the sympathetic ones are coming out alongside thoracic and lumbar, whereas the parasympathetic is cranial and sacral. Right, what does that take us to? Well, over on this side, we've got one that doesn't appear on the left. And although it's a kidney, it's what's sitting on the top of the kidney that's important, and that's the adrenal gland. Now, we have 2 kidneys, and on top of each kidney is an adrenal gland that produces adrenaline. Aha, makes sense. So the sympathetic nervous system, when that's stimulated, it will stimulate the adrenal gland to produce adrenaline. So that's what kicks off the adrenaline. We don't have an equivalent on the other side that stops it. You know, it's just when we stop needing it, this stops happening. Oh, I haven't touched the board for long enough. That's the trouble, sitting down. I have to sit down a bit at the moment. I wondered what the ooh was. Right. It's ridiculous that computers attached to the smart boards can do that, you know, because you can quite easily spend a while talking through something big. Never mind. Right, so yeah, adrenaline is one of those hormones that switch it on, switch it off. Okay, next one down is the bladder. Now, the parasympathetic will allow contraction of the bladder, so you can empty the bladder. However, the sympathetic actually inhibits contraction. It does relax the bladder, but you think, well, if I'm nervous, I constantly want to go for a wee. In a relaxed bladder, you know, you can obviously fill it, it'll stretch, but no, but this is the thing, it's less about the relaxing here, but it's more about the fact that it inhibits the contraction, so it actually, yeah, doesn't let you empty it properly. So, you know, you could be waiting for an interview and you can go for a wee half a dozen times and, you know, it's a teaspoonful at best, yeah? but the bladder is, it's a luxury item when it comes to dealing with stress. You haven't got time to go for a wee if you've been being chased by the lion. So, you've got to hold it so it does relax, but yeah. So that's the bladder. And then the other bit that we've got on here, sex organs, well, sympathetic nervous system works like adrenaline. Any degree of stress, they ain't working. All right, so if you're under stress, not tonight, dear. You need to be relaxed, So, no, if things need to be done, if the washing up hasn't been done, or there's good reasons, your parasympathetic nervous system needs all the help it can get. So you need to be relaxed in order for the nerves to actually supply the reproductive organs. Again, that's not something you stop and do while you're being chased by the lion. Right? There are a couple of things that don't appear on here, and I'm not sure which nerves would be involved. I'm guessing they'd be sort of distributed all over the place, but it's about blood supply to the skin and to the muscles. And if you think about it, those two don't necessarily need blood at the same time. If you're under stress, if you're being threatened, where does your blood need to go? To your muscles, so you can run away or fight. But it doesn't need to go to your skin. So when you're stressed, you go pale, don't you? So the blood's diverted away from your skin and towards your muscles. All right, so that you're making best use of what you've got. We don't run enough supplies to keep absolutely everything going at full pace all the time. It would be very wasteful, wouldn't it? It would be the same with the digestive system, for example. We don't produce all the enzymes and things that we need all the time. It would be wasteful. So we switch them on, switch them off, and that's really what all this is about. When you're relaxed, on the other hand, you don't need so much blood to your muscles, but, it can go to your skin, and that's fine. But it also explains why. If you're going to exercise, it's why you need to warm up. Warming up before exercise, of course, starts to stimulate the sympathetic branch of the autonomic nervous system, so that'll increase the blood flow into the muscles. You don't want to be relaxed when you start exercising. All right, the muscles need to have been used a little bit first so that you've got a good blood supply into the muscles. It doesn't need to be anything huge, just stretching them and things like that is adequate. But it's a matter of, making sure that part of your nervous system is getting the blood in there before you start exercising, rather than suddenly surprising it, because that's obviously where you can injure yourself quite easily, can't you? Just bursting into some activity without warming up a bit first. Okay, I think that's as far as we need to go with the autonomic nervous system, and that is, as I've done an awful lot of talking there. Right the way through the somatic nerves and the autonomic nerves. So you haven't got anything really, to refer to on that. So if you're thinking to yourself, I'm sure we did something on that. Yeah, it's all right. It's just that because it doesn't come up in the exam, I don't give you extra handouts, don't make notes on it particularly, but it's definitely worth talking about. And even if you haven't memorised every word I've said, if you have, then that's worrying in itself. You will know we've done it. You'll remember the homunculus and things like that, and you'll have a memory of this too. Okay, we will take a break at that point, and we will restart with the eye after break. So I think 11 o'clock for the eye. Aye. So we'll have a look at that, and see how far we can get with it. Okay.